Why don't we get started? Hello everybody, welcome to Science Friday. Science Friday is organized by Journal Club, which is an organization led by team students and faculty members who train new people to present scientific journals and, most importantly, provide a forum for database discussion. We take on almost any relevant issue that you're passionate about. If you want to be trained as a presenter or if you're a veteran presenter looking for a training, please email Anya and we will work with you to make that happen. I want to take a moment to acknowledge somebody on the journal.
How did we lose a person already?
This week it is Miles. Please give it up for his outstanding contributions and consistent engagement. The team is mentored by Dr. Paul Hauser and Luke D. There are 3 leaders. Akshay handles the training of people on our team, Anya handles the training of presenters, and I curate our talks and handle Science Thursday itself. This is how our meeting today is going to run. Today Mahtab is going to present for about 20 minutes. There'll be time for questions mid-presentation. Please type your questions into the chat as you have them. The simpler the question, the better. We will organize them, either call on you or ask the question for you if you prefer. We are recording this presentation to be shared via YouTube, so if you would not like your question to appear in the chat, please only private message your question to Akshay. During the presentation, we ask that you keep your cameras on and stay muted unless you're asked to clarify a question. Next week, we'll have a guest presenter and Ruta, but now please pick it up from Mahtab. Thank you.
Thank you everyone for coming, and when I share my screen, maybe I don't see your question at first, but I will respond to my promise in the end, okay? I will do my best to respond to your question while I'm presenting. So, here we go. You guys can see, right? Okay. So today I'm going to talk about my PhD dissertation in a way that is non-technical and give you some mathematical essence behind it. That's the purpose of this talk, to be give you some idea about my dissertation. So first thing I'm going to talk is about some mathematical concept or property that you may already use it, but you never pay attention or never pay attention in the details. So for example, the first one I choose, there is a duality, this geometric duality, which is very beautiful between a cube and an octahedron. So how is that duality is, if you have a cube and if you find the center of each face and connect the center of each face together, you will have the octahedron. And also if you have an octahedron and if you find the center of each face and connect them together, you will have the cube back. So that means octahedron and cube are dual of each other. They have this duality between them. Okay, so this is the concept of duality that we see in geometry. Is one example, of course. So if you consider the cube and you find the dual of the cube, you will come back to an octahedron. And if you have an octahedron and you take the dual again, you will come back to the initial one was a cube. So this property that you start with a cube and you took the dual twice and you come back to the cube again, we call it a reflexivity property. So as we talk, in the first slide, I talk about duality between them. And if you apply that duality twice for this set, which is you consider your set is cube, you're gonna come back to the cube as well. You start with cube and took the dual twice, you come back with the cube, which is the same as what you start. So we can say cube is reflexive. This property for cube, this duality for cube is a reflexive. Okay, so this is an interesting, a way of seeing duality, the reflexivity. For this duality in geometry. Okay, now another type of reflexivity that we may know, but we in fact maybe use it, is reciprocal. If you have reciprocal of any number, you will have that number back. So which is this, of course, when that number is not 0, because if it's 0, 1 over 0 is undefined, right? So that with all said, if you consider your duality will be a reciprocal and you start with set C, and you take the reciprocal and you take the dual again, which means reciprocal of what you have, which is reciprocal of reciprocal, you will have the C back. So here you have C, you start with C, you end up having a C back. So again, this is a somehow reflexivity for this duality of reciprocal, respect to that dual, if your dual is reciprocal. Okay, if you want to be technical, if I say all of real number are not reflexive respect to reciprocal. Why? Because there is 0 here, and 0 will not satisfy in this condition, right? So R is not reflexive. All of real number are not. But if you remove 0, and then R minus 0 is reflexive respect to this dual, because as you see, you start with C, you end up having C. So every single element in R minus C will satisfy in this fact. So that's the reason you would say R minus C is reflexive respect to duality of reciprocal. Okay, does it make sense so far, guys? I didn't look at the chat, but yeah, you can always say thumbs up. Okay, so another interesting reflexivity that you may know in calculus, and you may use it, is inverse function, reflexivity of the functions. So when you come, like, it's like related to functions, I mean. So if we have a function, and we know if we compose any function with its inverse, we have identity, means whatever is input will be the same as output here, right? So if you define your duality this way, that dual of F be F inverse and dual of F inverse be F, this F and F inverse are dual of each other, then if you have a set of bunch of these X and you affect F on those set, you will have a map of F of A. And if you take dual again over that set, which is F inverse, then you will have this F or inverse of A, which is A, you will have A back. So again, you will start with A, you end up having A while taking dual twice. So this set is a reflexive set. Again, it could be not reflexive if your function does not have inverse. If it's not inversible, there's no inverse, so it won't be reflexive. And if it is reflexible, if it is inversible, like you have an inverse, then you will have the property of reflexivity, because it's true for every function. Okay, so here we go about, like, so far I just talked about like a picture of duality and reflexivity and things like that. That is a very big picture in general in math. Like, we may use it every day, but we never notice it. Okay, so now before I provide more information about my dissertation, I have to give you some background. And for giving you some background, I have to define a bunch of mathematical concepts. So I would appreciate if you bear with me and I define this mathematical object, then I can tell you what I did with them in the end, okay? So the first mathematical concept is vector space. So vector space, so first talk about vector. What is a vector? Vector is an arrow with a length and direction. This red arrow here, this is one vector because has length, has a direction, so that's a vector. And we usually show him with U, V, W. And so if you have, for example, in this scenario, the one I have here, if you have two vectors, you can add, if you have two vectors, you can add them up and create the third vector, or you can stretch one of these each vector, and you can stretch it out or shrink it. So we call it a scalar multiplication. If you have this red arrow or red vector here, and you multiply it by some number bigger than 1, it's gonna be stretched out. So with that all said, if you have two vectors and keep adding them together and stretch them, you will create a vector space. So then vector space will be a vector that has two primary operation on it, which these two primary operation is, one is addition, you can add two vectors together, and the other one is a scalar multiplication, means you can stretch or shrink any vector. So that's we keep applying this property, you can create a vector space. Okay, Now you may say, what is the example of vector space? So example of vector space, these are the example. So for example, when your dimension is 0, you have a point. There's no vector technically. And when you have your dimension is 1, you have one vector, and you can add them together, stretch it, and you have a line. And when it's 2, you have two vector, then you can create, you keep adding them together and stretch them, and you can create the whole plane out of it. And if you have 3-dimensional, you will have shape like that. So, and there's 4-dimensional, that is very complex. And sometimes I can imagine, sometimes I cannot. So it's difficult to imagine. So, but in general, a line is an example of a vector space, a plane for 1 dimension. A plane is an example of a vector space in 2 dimension. And that the last one is the example of 3-dimension vector space. Okay, so now we know what is vector is and what is vector space is. Now we want to talk about what is linear transformation is. So a linear transformation is just a fancy word of telling is a function. So transformation is just means a function. A function from a vector space to other vector space means your input is a vector space and your output is a vector. So any function that your input and output is a vector space is a transformation. But now I said about linear transformation. So what that means, a linear transformation is when you have a linear transformation is a function that transfer any line to another line. So you can rotate the line, but every line will be transferred to another line. So line stay line. So that's the reason we call this transformation is linear, because line will stay a line. Maybe they rotated and maybe they're shrink or something like that, but still they are a line. Okay, so that's the reason we call it as a linear transformation. So a simple example of, as I mentioned, a linear transformation is rotation, because like you have this one and you're rotating like that. That's a very easy way to see. So I thought the most intuitive way that I can explain a linear transformation of a function is I think this is a very beautiful picture, which is if you have a projector. A projector is a linear transformation. Is a function that does a linear transformation. So how so? Because if you have this triangle in your projector, this line will stay a line. Maybe it just get a stretch, maybe the slope of the line change, but it stay a line to be able to have a perfect picture or the same picture that you see in the field. So that's a very good example of seeing a linear transformation. So. And what else? So now I talk about a linear transformation. I talk about a vector space, right? So remember, vector space was the space full of vector, and linear transformation was a function that transferred those from one space to other space. Okay, now the interesting thing, there is a duality between linear subspaces and linear transformation. So when there is duality, you always can define some sort of reflexivity. So if we know there is a duality between vector space and the function that transfer them, then there is also a similar idea between them, which is a reflexivity. If you have a bunch of vector space and you find the dual of that, which is the linear transformation corresponds to them, and you take the dual again, you come back to the same vector space. If that happens for your vector space, that means that vector space is a reflexive. And if it's not happening, means it's not reflexive. Okay, so that's a very interesting way. So this is very actually interesting definition. As I mentioned, this is not the technical way, but this idea was created by my advisor Paul Hamas in 1970, so many years ago. But it's still something that probably was there before. But you know, it's interesting to know where. That's a very important thing, actually, in operator theory, actually. Okay, so now we know there is a reflexivity between linear subspace and linear transformation. Now, what else I'm going to talk is what is Hilbert spaces, what is Banach spaces. So a Banach space is a vector space without hole that has a norm in it. So as a Banach space, if I want to simplify, is a vector space that you can have norm. What norm means? Norm is if you have two vectors, you can say what is the distance between these two vectors is, or you can even say size of one vector. So a norm just is like a ruler in the vector space that should say how two vectors are far from each other, or what is the size of one vector is. So Banach space, in a simple way, if I want to say, is a vector space with a norm in it, okay? So, but Hilbert space has telling you, and it has a norm, and even more, will give you the angle between two, not just tell you the distance between two vectors, will give you what is the angle between two vector is too. So you have more information in Hilbert space. So I showed as a protractor because here protractor does the ruler job and more, because you can say the angle between two vector as well. So that's how I try to show it. So that's the reason I would say Hilbert space is a Banach space, because it has the norm, which is ruler, and more because has an angle. It tell you about the angle between two vectors. Okay, does it make sense, guys, so far?
Sorry, I'm sorry to interrupt. I had a question about the previous slide. If you go back.
Yeah.
So I guess at least in linear algebra, the way we learned it was that the dual space was the space of linear transformations from a vector space to the field. Is there a reason why in this case it's
That's a very good question, actually. This one, that's something that I will work in this setting, but this setting is different with what you're telling. The dual space is involved, but as I mentioned, I'm not telling it technical. If you want, I can talk about that in more details after the presentation, okay?
Okay, cool.
Okay, so now after I tell about Banach and Hilbert space, I thought it's cool to show you the picture of Banach and Hilbert. So this one is Banach space. He's like here, he's probably young as age as you guys, and here is a Hilbert space. I just thought it's cool to see who they are. They are two important mathematicians in operator theory and functional analysis field. So. Okay, so the one thing I want to talk is convexity. That's another definition. So we say a convex, we can say a set is convex when for every two arbitrary points in the set, you can, the line that run between them is stay in the set. So if I want to show you a little bit more here, if I have two arbitrary points anywhere, so the line that is drawn between them stay in the convex. There is no two arbitrary point that you draw the line between them is not going to stay there. So this is a convex set. But this one is an example of event set is not convex because there's 2 points, as you see here and here, there's more than 2 points. So if you connect them together, if you draw the line between them, so it's not going to be completely in the convex set. So that is not convex. Okay, that's the 2 examples of one is convex, one is not. Okay, so what was my work was related to absolutely convex set. What absolutely convex set is a convex set that is a balance. What balance means there is a symmetric through the origin. So means there is this like there is symmetric through the origin from this convex set. So just I want to hear you remember absolute convex set is nothing except a convex set with a symmetric through an origin. Okay, because I want to apply it. Let's talk about it shortly. So like here is another example of this set is convex and also is balanced, which means has this balance through the origin, right? So that's the example of an absolute convex set. Okay, so here we go. Now finally, I told you enough to be able to tell about what was my work. So at least here I can say about my advisor work. So Don Harbin, my advisor, had this perspective So as we talk, there is lots of different theorem in reflexivity in Hilbert space. There's lots of notion, topology version, algebraic version. They add limits in it. So it's just lots of different version of the reflexivity exists in Hilbert space. So Don Hodwin in 1994, he devised a very general setting that study all sorts of this reflexivity at one body. We call it is a triple setting. So what happened, you can study all of this type of reflexivity at one body, which is the name of that big setting is a triple setting. Okay, so in that setting, this setting is very valuable because what he did, he could prove lots of important and well-known theorem in Hilbert space, but with a very shorter and elegant proof. So the proof, very large, like many pages of proof turned to be a one paragraph and is very nice and elegant and easy to understand. So, and his work was for, his proof was related in his setting was for Hilbert space, and he worked with linear subspace in Hilbert space. So that was what he did in 1994. He had that paper. Okay, so what I did, I generalized Don's work from linear space to absolutely convex set, and I work with Banach space, replace Hilbert space. So that was the big generalization because as you see that here is what he did. He worked in Hilbert space, I work in Banach space, which is you have less thing to work. Here you know about angles between two vectors, but here you don't know, you just know the norm and distance. And this one was a linear space. In linear space, you have lots of good property. You can add two vectors, you can scalar, and you have a scalar multiplication, but in absolute convex, you don't have any of those. The only thing you have is convexity and a little bit symmetric, that's all. So there you are losing lots of useful property and you still want to prove the same thing. So it's going to be harder to prove the same thing because you're missing lots of good property. Okay, so that was the big main thing that happened in my paper. And we proved lots of things that he proved in his paper. So, so what would be the application of this stuff, what I was talking about? So what the stuff I'm talking about in general, convexity is very important because in math, they usually like to find a structure somewhere. And when they find a structure, they really like to preserve it through a function, continuous function, linear transformation. So convexity is the really first structure that you can have in your set. And then if you can preserve it over a linear transformation or continuous function, it's gonna be something very valuable. So that they can apply it a lot in math is a very important thing. And another thing about the application you can see, when you have a convex set, so you have one minimum or one maximum. So when they apply in machine learning, so many times they're looking for like their point will be convergence to some solution. So when you have a convex body, so it's easy that the algorithm will have a solution in numerical way, which is something is valuable. And they like, of course, is important when they find a model of something. And another thing is what the application is, as I mentioned, when you generalize one theorem from the generalize that theorem, then you will, there's more setting. So you don't, for example, if your setting need A and B and C to apply that thing, you don't need B and C anymore. Anybody has just A can apply this stuff. So that means that more people can apply these theorems. You don't have lots of conditions. There is less assumption, and that's easier to prove. Not easier to prove, it's harder to prove, but it's easier to use. So, yeah. So now here, one other reason that I was interested in this research area was, so first of all, I was very fascinated by Don's triple setting, that how a new perspective could allow many well-known and important theorems to be proven in much shorter and much more elegant way. And he also have new results as well. But that was very fascinating. So everybody likes to have a shorter version of a proof rather than very long, many page of proof. So it's not that attractive. So that was one reason that I was interested in this work. Another thing was, I remember I had like some background in convex geometry, and I knew it's something valuable. So like I remember in my bachelor, even I remember my advisor gave me this paper and said this one is about convex function, and it's very, very valuable, especially in applied math. So I remember from that time that how valuable is convexity. So another thing, as I mentioned before, naturally I was interested to generalize those ideas, because when you generalize, more people can use your work, and it's better, it's more people would be interested in what you prove then. And then the last one is, of course, I knew is a significant generalization if you replace a linear subspace to absolutely convex set. It's very general, very significant generalization. So that made me to be more motivated, and I wanted to do it because I knew it's worth it. It's something interesting. So that's it all, guys. Thank you for your attention. Thank you.
Awesome. Do we have any questions?
Function? Yeah. Oh, yeah. I'm supposed to respond to that. Sorry about that. We had some questions in the chat, which I tried to answer a little bit, but maybe we get some clarification on this. There was some wonderings about how the fact that some convex sets are bounded might change the study of them, as opposed to linear spaces, which are infinite.
So you mean like if a convex set is bounded, then stay bounded in the other setting? When you have a...
I guess the question is how the study of Banach spaces and absolute convex sets is complicated by the fact that they aren't necessarily infinite.
I don't understand the question, so sorry. Can you repeat it?
I think it's because like some of the examples that you gave of absolute convex sets, for instance, just like a circle centered at the origin.
Yeah.
All of the elements, there's like the norm is bounded. Whereas when you have your linear subspace, because you can scale them arbitrarily, you can get elements that are arbitrarily large in your plane, for instance, or in a line.
Yeah.
So the question would be, I guess, is there any kind of intuitive way of understanding how that changes the study, or how that might complicate your work compared to the study of Hilbert spaces and linear subspaces?
Okay, so you want to have a little bit intuitive from how we extend the idea of linear. Okay, so the idea, if I want to say it like I try to tell it in a way that's really like understandable, would be something like, so my advisor setting, he would, for example, if you have a subset of X and this one is a linear subspace, so what would happen? He had like these elements of finding a pair, which would be all of those functional that you were talking is in the field, not is in the other operator, right? Remember you talked about like a dual. So there's like some element that there's like some functional, and functional, yeah, that's going to be a little bit technical if I want to say. The functional would be from X to a field, not because what I was taught in my talk, I talk about linear transformation from vector to vector. I call it like from X to X. That was my talk that you asked what happened for functional. So the functional will be something that gonna help to define something like a perp and pre-perp in the linear space setting, that we have this a pre-perp that like it's something like there's some functional that somehow kill all of elements in A. So we had stuff like that in DONS. But in mine, we replaced this one with a polar, which was all of those, finding the supremum of all of those functional in, as you said, in a finite set. Okay, and we have to make sure the supremum will be in the ball, less than or equal to 1. So we replace the idea of, like when we had this duality between those stuff, we replaced the idea of killing all of A with being bonded over a ball. So, and we replace the curve with polar, something like that. Yeah, it's going to be a little bit hard to explain, but I can try later harder.
So maybe, I guess I have a question on those lines, which is kind of back to the linear transformations, because I guess I was still a little bit confused about that. Is there an example of when the dual as being kind of all the linear transformations from a vector space to itself, when it would be reflexive?
Okay, that's a very good question, actually. This one, when I talk, should I come back to the slide or I don't need to?
I think it was a few slides down, right? The one where you give the example.
Yeah.
Yeah.
Exactly.
Mm-hmm. I know that in like a finite dimensional vector space, the dual of the dual, when you're talking about functionals, is the same, but I just wasn't sure when that would apply here.
Yes, that's a very awesome thing to know. What you say, the dual of the dual that I showed, the dual with the sharp, is the same as X. If it is the same as X, it will be a reflexive, exactly what you said. So this one you're talking is, we call it a classical version of reflexivity. So that's like proven for a long time. But this is stuff that is the relationship between duality, between linear subspace and vector space, is something different with that. This one is a classical version. This one is proven by Paul Hummus at 1970. So that's a very brand new thing and is very technical than what I wrote here. So for example, your vector space has this property of being invertible. Means like they are like all of those vector space that keeps some property inside of themselves. And then these are all of those linear subspace that correspond to them. And again, you come back to all of those vector space that stay in the set. So they're a little bit technical, but I removed them all and I just wanted to show you the big picture. Yeah. If you want, I can maybe talk about like a double dual later in a more technical way.
Okay. Awesome. Thank you so much, Mahtab. I know we have an all-school meeting now, so students and teachers, I'm afraid it's time to leave. If you have any questions or if you want to reach out, please let us know. If you want to present, you can reach out to Anya. Thank you, everybody, and I hope to see you next week. Bye.
Thanks, Mahtab.
Thank you for coming.
Actually, if you wanted to have to talk about those terms more, we can talk later today. But